it's on. Hello, good morning. I need to say a few words instead of Martin. I work in Copernicus Atmosphere Monitoring Service, and we are producing air quality forecasts for whole Europe. But the resolution of this forecast is coarse, especially for people who are interested in urban air quality. So Martin and Johannes, our commenters from the Heron Institute, actually came up with this proposal that we try to see how much extra value we can extract from this raw coarse resolution air quality forecast by introducing other data sets. There are a lot of data sets that you can use, and the challenge of the team was trying to experiment, to see what is available, what they could use, and how much they could improve what our raw forecast skill is. So I think that's my introduction, and I will leave it to you to explain in details what you've done.
Thank you.
All right, so thank you, Micha, for your introduction, and also thank you to Martin and Johannes, who are joining online, for their mentorship during all these 4 months. So, as Micha explained, our objective was to downscale CAMs. And when we first tried to solve the challenge, we first focused on getting data on observation sites as good as we could. So in order to do that, we have several data sets. So we would have the CAMs reanalysis. We focused on the NO2 pollutant, which is a grid of 10 kilometers resolution. Then we have the actual measurements from the European Environmental Agency, which were used to train and validate, and some extra data sets, such as topography, land use, meteorology, build height, population, or even roads. The final product of this first approach are the time series that we can see on the right. So here we can see our model in red, the 10-kilometer CAMs in black, and the actual measurement in blue. We can see that our model successfully reproduces quite well the actual measurements, while the raw CAMs, or the CAMs at 10 kilometers, normally underestimates the actual measurement. So this was our first model, and in order to train it, we used an 80-20 split of the data sets, but not on the station level, but instead on the hour level. So all stations or all measurement sites from the EA were used for both training and validation, which is why we were able to obtain such good results. We then focused on validating this model, and we used the Fairmore principles. We used some target diagrams, which, to be super fast and it's super easy to understand, each dot that we see is a station. And we need all stations to be inside the blue circle. The best model is the one that has all the dots at the origin, at 0, 0. On the left, we see the target diagram of CAMs interpolated, so the CAMs at 10 kilometers. And we see that it's actually quite good, because all the dots are inside the circle. But they are quite far away from the origin. On the right, we can see the results for our model. What we have achieved, actually, is a bias reduction of the CAMs at 10 kilometers. Then we played around by testing different data sets. So training the model using different data sets to see how these data sets improved or worsened our model. So for example, model version 1091, which is this one over here, has all the data sets. Instead, version 1061 only has topography. In red, on top, we can see the MQI, which is an indicator and is actually the distance between each dot and the origin of the 10-kilometer CAMs. We can see it's quite high, it's near 1, while our model is around 0.5. We saw that there are no significant differences between model versions, which is in part due to the fact that 0.5 is already under the model uncertainty, so we could not improve that any further. So finally, we tested our model in different regions. So on the right, and I know you can see it very small, we can see the MQI for different model versions, so different data sets used, at different cities in the Iberian Peninsula. We can see that the cross would be the 10-kilometer camps, and the dots are our model. We can see that our model is normally better, or is always better than the 10-kilometer camps, and that in some cities the improvement is higher than in other cities. And we also tested that in Poland. We saw that the improvement is more or less the same. We also tested that in Italy, and the results were similar, so we can say that our model generalizes well throughout Europe. Finally, we compared this MQI to the ones obtained from the CAMS European Air Quality Forecast optimized at observation sites product, which has an MQI of 0.3 and 0.5. So if we compare this MQI with our MQI, we can see that we actually don't worsen the actual product. We don't improve it either, we are on par. So next on, we tackled the next challenge, which will be explained by Oscar now.
Thank you. So until now, we have been talking about our model trying to improve the concentration of NO2 at observational sites. But now we wanted to generalize this machine learning model so as to get grid information, which is indeed the aim of the challenge. So, in this approach, we wanted to downscale this CAMS reanalysis data, which is 10 with grid spacing of 10 kilometers, to urban resolution with a grid spacing of 100 meters. So in this case, so as to validate the model in this new approach, we used a different split of data for training and validation. So instead of using an hour split, we used some stations to train the model and some other stations to validate the model. And let's see. So as an example, here we have the city of Barcelona, and here in the left we can see the raw CAMS product, the 10 kilometers product, and then after the downscaling we get this 100 meters map of the city with the concentration of NO2. So to do that, we needed to do some attempt with different model versions. Here, this first image is the first attempt with a model version which doesn't use any extra feature, doesn't use any extra data set. So that's why we cannot recognize the structures of the city. Then we added the topography, and here we can see more or less the urban area and the mountain area behind Barcelona. Then we added also the information of population of the city, and here we can see better the different neighborhoods. And finally, we added also road information and building height information, so as to get this most complete version of the model. So as an example, here we can see a satellite image of Barcelona where we can identify those structures which are taken into account by the model so as to get this concentration map. For example, we can see that the model can identify the city center, which is the area of the city with higher amount of traffic. We can see also, for example, these mountain areas around the city and also this Montjuic hill inside the city. We can also see the city port where the concentration, the NO2 concentration is higher. And also we can see some farmland, like the agricultural park of Baix Llobregat, where we can see that the model can identify it due to the fact that it uses also land use data. And the model can also recognize some city highways that surrounds the city, like Ronda de Dalt and Ronda Litoral, which are those two highways. So then, once we got those maps, we wanted to validate also the model. So we got some target diagrams. Here we have the target diagrams for one of the versions. We can see, as expected, that the values are not that close to the origin of the diagram because we didn't use the same splitting method. Now we're trying to get values in a place, in points where no observational data. And here we can see that in this graph, so we can see that most of the versions don't improve the 10 kilometers CAMS product, but those that have all the data set can even improve these 10 kilometers CAMS interpolated. We can see that here as a difference, here we can see a high difference between the different model versions. We can see that the better one is this one. The icons are a little bit moved, so this 2091 corresponds to this this version which has all the data sets. And finally, we got also this this diagram where we can see that now the cross, which corresponds to the row CAMS product, has more or less the same MQI of the different versions of our model, but here we can see that versions are more splitted, so we can see that in general the version 2091 is that one that improved the most the row CAMS product.
Okay, so we have seen what our model achieves in terms of downscaling, what were our results. Now I'm going to present the methodology we followed to achieve this. So we followed more or less a standard machine learning methodology. First, we developed a machine learning model for regression to predict the NO2 values. And we integrated different sources of data, mainly the air quality stations. Yeah. Higher? Like this? Like this?
Yeah, put it higher on the line up. That's it.
Okay, thank you. So, yeah, mainly the air quality stations, and then we also added external data sets, such as the topography, the methodology, population, among others. Then in a second step, we performed the validation, which we already presented. And we used the fairmost standards to validate our model. So we divided this process into four steps. First, the data integration, which includes the interpolation of the data sets to the desired resolution, and then also the preprocessing of the data. Then the training of the machine learning model, then the inference to this grid space, to this desired grid space, and finally the validation. So let's start with the model specifications. We targeted the NO2 pollutant with a time resolution of 1 hour during the time period of 2022. And we selected 3 regions, which are the Iberian Peninsula, Italy, and Poland. inside these regions, we selected the areas with higher density of stations because of two reasons. Because first, we assume that these regions are actually the urban areas that we want to target, and secondly, because our model works better when we have high density of stations, so we want to focus on these areas with high density of stations. To do that, we employed a clustering algorithm to identify those high density of these regions of high density for these three regions that we have studied. So then, once we have these identified regions with high density, we proceed with the training, and to perform the training, we selected one station for each cluster, and then we evaluate the model at this station, and we use all the other stations, all the remaining stations, to interpolate and extract additional features for the model. So we do this interpolation, we integrate all the external data sets at the evaluation point, so the point for which we have selected the evaluation station. And finally, we train a regular regression machine learning model to predict the value at the evaluation point. We repeat this procedure several times, selecting different stations, and for all the time period we have selected. Once we have the model trained, we proceed with the inference. During training, we have trained the model with at evaluation points, but here we want to obtain a final downscaling product, which involves a grid. So here we do instead is we start with the CAMs, and we interpolate the CAMs values using bivariate spline to the desired resolution, which is 100 meters. We also perform interpolation for the stations. In this case, we employed nearest neighbors for the stations to the same resolution we want. And we also do the same process for all the data sets, all the external data sets. So we have, for all the products, the desired output resolution. We integrate all this data, and we input each point in the grid to the model to obtain the final product, which is the downscaling application. So finally, the validation, we follow the fair mode standards, which we already have presented the results according to these standards. So going directly to the future work, first, we think that it's good to study other interpolation methods because, as I said, for example, we use nearest neighbors, and this can be appreciated in the results in these lines that, in the shape of polygons, they are appreciated in the results, so we can study other interpolation methods which do not present discrete behavior, such as kriging, for example. Then we think it's important to work in improving the features that we actually have integrated to the model. For example, we have thought that we are using roads, we are using a binary indicator of where there is a road or not, but we could also improve that in a way that for each grid point we have the distance to each point to a road. Or the last possible future work is to study the model in other regions, but also during other periods besides 2022. Thank you very much. This was our project, so now it's time for the questions.